Hi all. In previous video, we saw what is conductors and what is drift velocity, how they are related with electric fields, and then we saw what is Ohm's law in point form. So Ohm's law in point form is given by J is equal to sigma into E. So where sigma is a conductivity of the material, and as temperature increases, this conductivity starts to decrease. The conductivity and resistivity are inversely proportional to each other. So next we will see, in this video we will see what is resistance and what are the properties of conductors and what is relaxation time in any material. So next we will see what is resistance of a conductor, what is the expression for resistance of a conductor. Now consider a conductor which is having a length L. So which is having a length L. The potential is applied, the external potential is applied is V. The external potential applied to this conductor is V. Now when I apply external potential to this conductor, so there is a movement of electrons, there is a field created in the conductor. Because of this field, there is a movement of free electrons. These free electrons will be moving in the opposite direction of the fields, right? So these free electrons will be moving in the opposite direction of the field. So direction of the current now will be in the direction of the field. So direction of the current will be in the direction of the field because the direction of the current is considered as a direction of the movement of positive charges, not negative charges. The direction of the current is taken in the direction of the movement of positive charges. So it should be opposite to the movement of the electron. It should be opposite to the direction of the movement of electron. So the current in the conductor, flow of the current in the conductor is in the direction of the applied electric field. So if I consider the electric field is in this direction, then the electrons are moving from this end to this end. The current will be moving from here to here. So direction of the current will be in this direction. Now I am already considered the length of the conductor is L and the surface area of the conductor is S. I am considering the surface area of the conductor is S. And I am also assuming that the current is normal to the surface area. The direction of the current is normal to surface area. Now, we know that the equation for electric field intensity due to a point charge is given by Q by 4 pi epsilon naught into R square. Q by 4 pi epsilon naught into R square is the expression for electric field intensity. Similarly, we know that expression for potential V is given by Q by 4 pi epsilon naught into R. So we can say E is directly proportional to 1 by R square and V is directly proportional to 1 by R. But from these observations, that is E is directly proportional to 1 by R square and V is directly proportional to 1 by R, from these observations we can write the electric field intensity is equal to V by the length of the conductor. Electric field intensity, that is magnitude of electric field intensity, is equal to V by, that is potential, divided by length of the conductor, because there E is directly proportional to 1 by R square and V is directly proportional to R. The difference between the E and V is 1 by R. So we can write the magnitude of E is equal to V by L, that is the length of the conductor. Now we know that the current flowing through any surface area can be written as I is equal to J dot ds. I is equal to surface integral of J dot ds. Now I am considering this current is normal to surface S. So when the current is normal to surface S, so it is in the direction of the vector normal to S. It is in the direction of the vector normal to S. So if I consider vector is normal to S is in this direction, then vector an cap is the vector which is normal to this surface, then the angle between I and A n cap is 0. The angle between I and A n cap is 0. So dot product between J and ds, dot product between J and ds is equal to maximum. So because the angle between them is 0, theta is equal to 0. So J dot ds is equal to J into ds into cos theta, or J into S into cos theta. You can, so J into ds into cos theta. So you'll, theta is equal to 0, cos 0 is 1. So you'll get J ds. So I can write I is equal to surface integral of J dot ds. So when the J dot ds, the angle between J and ds is 0. So you will get J surface integral of J ds. So integration of ds is S. So you will get the current normal to the surface area S is J S. The current, the integration of J ds over the surface S is S. So it is J into S. The magnitude of the current over the normal to the surface S for the conductor is I is equal to Js. So we know that, so this is the expression for current I is equal to Js. But we know that according to Ohm's law, that is point form of Ohm's law, we can write J is equal to sigma into E. J is equal to sigma into E. Right? So according to Ohm's law, we can write J is equal to sigma into E. Now, so what is E? Substitute E is equal to V by L. We know that E is equal to V by L. Substituting here, we will get J is equal to sigma into V by L. J is equal to sigma into V by L. Now, what is J? So, from this equation, you can write J is equal to I by S. So, J is equal to, substituting J is equal to I by S in this equation, you will get I by S is equal to sigma V by L. So I by S is equal to sigma V by L. Now rearranging this, you will get V is equal to IL by sigma S, or L by sigma S into I. So this is like the equation for Ohm's law. V is equal to I into R. So I into R. So this is the constant term into I. The V is directly proportional to I. So L by sigma S is the constant term. So we can write V is equal to L by sigma S into I. So if you equate this equation with the equation of Ohm's law, then Ohm's law in normal form, not in point form. So in normal form, V is equal to I into R. So we can write R is equal to V by I, which is equal to L by sigma S. So R is equal to V by I, which is equal to L by sigma S. So which is called, this R is called resistance of a material. So if you compare this equation with Ohm's law, which is equal to V is equal to IR, so R is equal to L by sigma S. So in the place of sigma, I can write sigma as 1 by rho. So this equation will become rho C by L, rho C into L by S, where rho C is the resistivity of the material. So I can write, so rho C into L by S. That is, in general term, if you say R is equal to, you know that rho L by A. So rho L by A, so is the equation for resistance in terms of resistivity. So here I am taken area as S. So the equation is rho L by S is the resistance equation. So next, this is the equation for resistance in a conductor. Next we will see what is the property of a conductors. The properties of the conductors are, first properties. So all the properties are conductors are considered when the conductor is in static the position, when the conductor is in static position. Under static condition, though there is no charge and no field can exist within the metallic conductor. So if the conductor, there is no charge or no field can be exist inside the conductor. So if the charge is 0, then charge density inside the conductor is 0. So we can say in a static condition, there won't be any charge or field exist within the metallic conductors. So but in the surface of the conductor, there can be a existence of the charge. So we can say in a conductor, there will be a surface charge density, there won't be a volume charge density. But the surface distribution of the charges will be depends on the shape of the conductors. And for an ideal conductor, the conductivity of a conductor is an infinity. For an ideal conductor, the conductivity of a conductor is infinite. And on the surface of the conductor, we will say that the conductor will have equipotential surface. The conductor surface is an equipotential surface. These are the some properties of the conductor. First one is there won't be a charge inside of the conductor. So charge density of the conductor inside the conductor is 0. The charges can exist on the surface of the conductor. So we can say there will be a surface charge distribution, but it depends on the shape of the conductors. And the conductivity of ideal conductor is infinite, and the conductor surface is considered as equipotential surface. So next we will see the one more term related to medium. It may be conductor or it may be dielectric. So which is the term called as relaxation time. So this time, the relaxation time is depends on the decaying of the charge density. So if you have the charge density, what is the time taken to decay for some position of the curve, so it's called relaxation time. So it depends on different types of the medium. So there are two types of the medium. One is homogeneous and other one is non-homogeneous. So what do you mean by this homogeneous medium is, if the property of a material is same for all the points, if you take any point of material, then you will get same property, then that type of the medium is called homogeneous medium. And other medium is non-homogeneous. Non-homogeneous means if the properties vary from point to point, then that type of the medium is called non-homogeneous medium. And one more other two types category is linear and non-linear type mediums. So linear type medium where flux density, that is D, is directly proportional to field intensity. That type of the medium is called linear fields or the linear medium, where flux density is directly proportional to field intensity. Then that type of the medium is called linear if this case is not satisfied, that is flux density is not proportional to the field intensity, then that type of the medium is called non-linear medium. So this relaxation time is mainly applicable for homogeneous and linear type of the medium. So this relaxation time mainly defined for homogeneous and linear type of the medium. So relaxation time is given by the term depends on the charge density. So if in a homogeneous and linear material, the charge density is given by volume charge density is equal to rho naught e to the power minus T by tau, where tau is minus sigma by epsilon. So it depends on conductivity and the absolute permittivity of the medium. So tau is epsilon by sigma. So this tau is called as relaxation time of the material. This tau is called relaxation time of the material, and rho naught is the initial value of charge density. The rho naught is the initial value of the charge density. If you see this equation, the rho is decaying in nature. So the charge decreases as time passes on. So relaxation time is defined as time required by the charge density to decay to 36.8% of its initial value. It's the time required to decay to 36.8% of rho naught. So that is called relaxation time. So relaxation time is very small for a conductor. So for a conductor, relaxation time is very small. So we can say that the charge density inside the conductor will decay very soon. So we will say there won't be any charge density inside the conductor, because the relaxation time for a conductor is very small. The relaxation time is tau is given by absolute permittivity divided by conductivity of the material. So in next video we will see what is properties of dielectric materials. Thank you.